In this section, we'll delve into the mysterious and ancient relationship that exists between limits and infinity. As you calculate various values of f and evaluate different functions, you can come across some bizarre things. For example, take a look at this function. F of x equals the fraction 2x plus 1 divided by the quantity x minus 3. Now, if you plug in 3 to this, you're going to get 7 divided by 0. Now, I know we've seen 0 divided by 0 in a lot of previous examples, but we've never seen a non-zero number divided by 0. Well, that's bizarre, I know, and it indicates something important. In fact, whenever you substitute a number into a function and get a non-zero number divided by 0, it indicates the presence of a vertical asymptote. And this holds true for this function. Let's take a look at the graph of f at x equals 3. Well, remember, an asymptote is a line which a function cannot reach. Here we have an asymptote at x equals 3, because when we plugged 3 into f, we got a constant divided by 0. Now, by examining the graph of f, we can see that the limits as x approaches 3 from the left and right are different. As you approach 3 from the right, f gets infinitely large, so we can say that the limit as x approaches 3 from the right of f of x is infinity. However, as you approach 3 from the left, f of x gets infinitely negative, so we say that the limit as x approaches 3 from the left of f of x is negative infinity. Vertical asymptotes aren't the only asymptotes which relate to infinity. Horizontal asymptotes do as well, just in a slightly different way. To see this, let's look at the graph of f again. Now, as x gets infinitely large, or as we go along the x-axis, note that the graph of f is bending slowly downwards towards a height of 2. Now, if a graphical argument is not enough for you, take a look at this chart based on the function values of f. As x gets larger, f gets closer to 2. Now, mathematically, this means that the limit as x approaches infinity of f equals 2. By the way, the limit as x approaches negative infinity of f also equals 2. As we travel left along the x-axis, the function approaches the same height. When I was explaining the last example, I said that x was getting infinitely large, and we translated that mathematically as the limit as x approaches infinity. Now, this type of limit is called a limit at infinity. If this limit exists for a function, then that function possesses a horizontal asymptote at the height given by the limit. Now, that's a lot of gobbledygook, but it's very simple in practice. Limits at infinity are very easy to calculate. All you have to do is compare the degrees in the numerator and denominator of the given function. By the way, the degree is the highest exponent. So, if we take a look at f again, we'll notice that the highest degree in both the numerator and denominator is 1. Because remember, if we don't write a power, it's inferred to be 1. Now, in this case, the degrees of both the top and the bottom of the fraction are equal, and therefore the limit at infinity of this fraction is going to simply be the coefficients attached to those highest degrees. Again, sounds like a lot of gobbledygook. We just take the coefficients of those x terms to make up the limit. Therefore, the limit will be 2 over 1, and we say that the limit as x approaches infinity of 2x plus 1 divided by x minus 3 is 2. And remember, we already know from the graph of f that the horizontal asymptote is 2, so it checks out. Now, what happens if these degrees are unequal on the top and bottom of the fraction? Well, if the denominator's degree is higher, then the limit is 0. But if the numerator's degree is higher, the limit doesn't exist, because it's infinity. In conclusion, if the limit as x approaches c of f of x is infinity or negative infinity, then f has a vertical asymptote at x equals c. Whereas, if the limit as x approaches infinity of f of x equals d, then f has a horizontal asymptote at y equals d. One word of caution. When we say that a limit equals infinity, we're actually saying that that limit technically does not exist, because limits have to be a real number. Therefore, it might be more enlightening to say that the limit does not exist because it increases infinitely, rather than saying that the limit equals infinity.